Good day everyone. Today, we'll be discussing a key concept of engineering design. At its core, engineering design is a blend of creativity, technical expertise, and problem solving. Engineers leverage this process to create solutions that fulfill specific requirements. It's about innovation but also about structure and methodology. In this presentation, we'll explore what makes engineering design so crucial as well as how it integrates with system engineering, concurrent engineering, and control systems. So my name is Micaela Villapana and I will be the first presenter of this topic. First will be the preview. Engineering design is a fundamental aspect of the engineering discipline, combining creativity, technical knowledge, and problem-solving skills to develop innovative solutions that meet specific requirements. Managing engineering design effectively involves understanding the processes, methodologies, and criteria that influence the development of products and systems. This report delves into the nature of engineering design, system engineering, concurrent engineering, control system and design, and the criteria that guides the design process.
Learning objectives. This report aims to achieve the following learning objectives. Gain a thorough understanding of the principles and practices involved in engineering design. Learn about the essential components and methodologies in system engineering and new product development. Understand the benefits and applications of concurrent engineering in the design process. Comprehend the importance of control system in ensuring design quality and compliance. Identify and apply critical design criteria to ensure successful engineering outcomes.
Good day everyone, I am Ransel Shanko, reporting the nature of engineering designs. The nature of engineering design is centered around solving real-world problems through the creation, development, and refinement of solutions. It's not a one-step process, but an iterative one, where ideas evolve into practical and efficient designs. In the first line, problem-solving focuses. Engineers identify challenges and create solutions from building structures to developing software. One of the key aspects of engineering is not a problem-solving focuses. Engineers are constantly identifying challenges, whether it's constructing a building, designing a piece of technology, or developing a software, and then working to create innovative solutions. Next is iterative process. Design involves cycle of ideation, prototyping, testing, and refinement with feedback driving improvements. Another essential component is the iterative process. Engineering design is rarely perfect on the first try. It's involved a multiple cycle of ideation, prototyping, testing, and refining. Feedback from this stage is used to drive improvements, ensure that the financial design balance key constraints like functionality, cost, safety, and environmental impacts. Now, let's take a closer look at the few other important aspects of engineering designs. Number 3, creative and analytical thinking. Engineers combine creativity and analytical thinking. Creativity is essential for generating innovative solutions, while analytical skills help evaluate feasibility and optimize designs. Number 4. Multidisciplinary collaboration. Engineers is not limited to just one field. Successful projects often require collaboration across multiple disciplines, such as mechanical, electrical, material science, and even programming. And number 5, constraint-based design. In the real world, engineers must consider various constraints. These include factors like feasibility, cost, time, safety, and ethics, and environmental impacts. Design must balance this to ensure they are practical and sustainable. Number 6, systematic approach. Engineers follows a systematic process that begins with defining the problems, conducting research, generating concepts, and moving through detailed design and prototyping before finally implementing the solution. 7. User-centered. Modern engineer design prioritizes the user experience. Engineers ensure that solutions are intuitive, accessible, and tailored to meet the needs of the end user. Next, number 8, risk and uncertainty management. Engineers always account for risk and uncertainties by planning ahead. They aim to minimize risk, focusing on aspects like safety, reliability, and performance. Number 9, trade-offs and optimization. In many cases, engineers must take trade-offs between competing factors such as cost versus quality or speed versus safety. The goal is to find optimal balance that delivers the best overall performance. And last, number 10, innovation. Lastly, engineering is always pushing the boundaries of what's possible by integrating new materials, process, and technologies. Engineers drive innovation and help advance modern technologies.
Now let's move on to system engineering and its role in new product development. System engineering is an interdisciplinary approach ensuring successful design, integration, and management of complex systems throughout their life cycle. So it focuses on addressing the entire system as a whole rather than just individual components, ensuring that everything works together seamlessly from start to finish. The key focus in system engineering is the early identification of customer needs and functionality that the system or product must deliver. Once we understand these requirements, the process moves into the phases of design, synthesis, and validation. This synthesis approach ensures that as we develop new products, we are not only solving the problems at hand but also considering how the system will operate throughout its entire life cycle, balancing performance, cost, and reliability. System engineering plays a crucial role in new product development, especially when dealing with large scale and complex products. By addressing issues early on and using a structured methodology approach, it ensures that the product will meet the demand of both the customers and the broader system in which it will operate. Next will be the key complex of computer engineering. First, requirements engineering. It established and manage system requirements. So, the first crucial step is requirements engineering. The first critical step is requirement engineering. This involves establishing and managing system requirements. We begin by identifying what the system needs to accomplish based on the stakeholder input. Then, we ensure that these requirements are maintained and adjusted as necessarily throughout the project lifecycle. It's about defining the problem before jumping into a solution. Second is the system architecture, design and overall system structure and relationships. Once the requirements are in place, we move to a system architecture. Here we design the overall structure of the system and determine how various subsystems will interact with each other. It's like building the blueprint for a house before laying the foundation. It ensures that all components fit together and communicate effectively. Third will be integration and testing. The next phase is integration and testing. After the individual subsystems are designed and built, we combine them and test the complete system to ensure it meets the original requirements. This is crucial step where we can where we can catch and address any issues, ensuring the system functions as intended. Next is the life cycle management. Finally, we have life cycle management, which focuses on managing the system from its initial design to eventual decommissioning. This includes updating and maintaining the system over time, ensuring it stays relevant and functional as new requirements or technologies emerge. Effective life cycle management keeps the system adaptable and sustainable over its entire operational lifespan. New product development and system engineering. New product development refers to the process of bringing a new product from concept to market. It involves everything from brainstorming ideas, designing the product, prototyping, and testing, all the way through to launch. The goal is to ensure the product meets both customer needs and market demands while staying competitive. Also, system engineering plays a critical role in coordinating the various disciplines involved in product development. It ensures the product development process is well organized and that each part of the system works together seamlessly. System engineering helps synchronize efforts across different teams such as software, hardware, and design to ensure that every component of the product integrates properly. So this approach reduces errors, improves communications, and ensure the final product meets its performance, cost, reliability goals. It is all about ensuring a smooth transition from concept to launch while managing the complexities of the development process. So the stages of NPDs, as you can see, we have idea generation, screening and evaluation, concept development. Next will be the product design, testing, and finally the commercialization. Idea generation, this is the initial stage where ideas for new products are created. Ideas can come from various sources, including customer feedback, markets research, internal brainstorming, or competitors analysis. The goal is to come up with innovative solutions that address customer needs or fill a market gap. Next stage will be screening and evaluation. Not every idea is worth pursuing. In this stage, potential ideas are eventually based on feasibility, market potential, and align with business goals. This also helps filter out unfeasible or unprofitable ideas early on to save resources. It's a critical step to ensure only viable concepts move forward. Next is the concept development. Once an idea is selected, it's expanded into a detailed concept. This includes defining the product's features, target market, and value proposition. The concept is then tested with focus groups or market research to gather feedback and further define the idea before moving into actual design and development. Fourth will be product design. After the concept is solidified, the product moves into the design phase. Here, engineers and designers work together to create the physical or digital design, including technical specifications and prototypes. This stage is where system engineering becomes critical to ensure all parts of the product functions properly together. Next will be the testing. With the work prototype, the product undergoes testing to ensure it meets performance, safety, and quality standards. This includes both internal testing by the development team and market testing to gather user feedback. Testing helps identify any flaws or improvements needed before the product is finalized. The last one will be commercialization. Once testing is successful, the product moves to commercialization. Sorry. This involves scaling up production, launching marketing campaigns, and preparing for the product's entry into the market. It's the final stage where the product is made available to customers and begin generating revenue.
Today, I'm discussing about concurrent engineering. Concurrent engineering overview. Traditional engineering. Product design typically takes longer than expected due to a sequential approach. Traditional engineering typically follows a linear process where each phase is completed sequentially. This often leads to extended timeliness as each stage must wait for the previous one to finish before moving forward. Concurrent engineering, a simultaneous approach to design and development that reduces time to market, improves productivity, and lower cost. This integrated approach encourages collaboration among cross-functional teams, including design, manufacturing, and quality assurance. Definition of concurrent engineering. Simultaneous engineering, different stages of product development occur at the same time. Benefits. Reduces design rework and enhances right the first time outcomes. Challenge. Initial implementation can be complex but offers long-term competitive advantage. The main objective of concurrent engineering is to reduce time to market while enhancing product quality and minimizing cost. This collaborative environment encourages innovation as diverse perspectives contribute to creative solutions. Advantages and disadvantages of concurrent engineering. Advantage. Multidisciplinary collaboration, faster design process, increased productivity, and competitive advantage. Disadvantage. Increased risk of errors, more planning time. Moreover, concurrent engineering can improve product quality as early identification of potential issues can lead to timely revisions. One major disadvantage is the complexity to introduce in project management. Coordinating multiple teams and assuring alignment on objectives can be daunting, leading to potential miscommunication. Concurrent processes. We have 7 concurrent processes to develop a production and delivery. Number 1, manufacturing process concept development. Number 2, manufacturing process development. 3, system level design. 4, subsystem design. 5, component design. 6, delivery development. And 7, service development. Concurrent processes is a crucial concept in optimizing production and delivery systems. It refers to the simultaneous execution of multiple tasks or operations that enhance efficiency and reduce lead times.
Hello, good day guys. I'm Giancarlo Bagol and let's talk about control system in design. First, importance of control systems. Control system is designed to ensure that the final product meets the desired specifications and functions are intended. They provided a framework for monitoring and regulating the design process, enabling designers to identify and correct issues before they become critical. Now, let's talk about control system in the engineering design. Control systems are everywhere from regulating the speed of an electric motor to controlling the temperature of a furnace. Designing this system requires a careful balance between input and process and feedback to maintain desired output under varying conditions. In many ways, control systems are the backbone of modern engineering solutions because they ensure that design perform reliability, and meet strict specifications. Now, let's talk about engineering design controls. First, design planning. Define project objective, deliverables, and milestone. Design planning establish what the project aims to achieve, what needs to be delivered, and key milestone or deadlines. Second is design inputs. Specify functional, safety, and legal requirements. Design inputs identify and define the necessary requirements, including functionality, safety, and compliance with legal standards. Third is design outputs. Create documents, drawings, and specifications that detail the final design. Develop detailed documents, drawings, and specifications that describe the final design of the product or system. The fourth is design review. Regularly evaluate the design process to identify issues early. Design review conduct regular evaluations of design progress to catch potential issues or mistakes early on. So the fifth one is design verifications. Ensure design output meet the input specification. This check if the design outputs match the input requirements. So the sixth design is design validation. Verify the product meets user needs in real or simulated scenarios. And design validation is to ensure that the final product meets user needs either by testing it in real-world conditions or through simulations. So for the seventh design is design transfer. Transitions the design to the development or production teams. This hand over the design to development or production teams for implementation or manufacturing. So the last design is design changes. Manage modification to prevent introducing errors or non-conformities. This manage any changes or updates to the design carefully to avoid introducing new errors or problems. So next is, let's talk about system design in control system. First is requirements analysis. Understand functional and non-functional demands from stakeholders. Understand the functional, what the system must do, and non-functional performance, security, usability, etc. Requirements from stakeholders to ensure the system meets their expectation. And for the second control system is system architecture design. Break the system into components, modules, and subsystems and define their interaction. System architecture design is decompose the system into individual components, modules, and subsystems and define how they will interact with one another. The third one is integration planning. Plan how subsystems will integrate, ensuring compatibility and communication. This develop a strategy for how subsystem will work together, ensuring smooth communication and compatibility between different parts of the system. And the fourth one is risk management. Identify and mitigate risk during the design process. This identify potential risk in design and development process and create strategies to mitigate or eliminate those risks. So the fifth, prototyping and simulation. Create models or prototypes to test system design before full-scale development. These build models or prototypes to test and validate aspects of the system design, allowing for adjustment before full-scale development begins. The last control system design is interface design. Manage interaction between subsystem and components. This focus on how the various subsystem and components will interact, ensuring seamless communication and function between them. Next is Quality Function Development or QFD. QFD is a team-oriented management techniques that aligns product development with customer expectations. So, example, a company is developing a new smartphone and wants to ensure that it meets customer expectation while reducing development time and improving market success. Key benefits is early detection of conflicts, identify conflicting features or needs early in the process, allowing issues to be resolved before production. Key benefits is early detection of conflicts. The team can resolve the display versus battery life issue by researching more efficient display technology or adjusting the design to include a large battery. This prevents delays later in the production. So for the outcomes, product enhancement improves product quality and performance. Increased client satisfaction ensures that final project meets or exceeds customer expectations. Shorter development cycle speeds up the overall product development process. Larger market share. A customer-focused approach leads to better market positioning. So the last part of control system and design is we have QFD 4 phase. First is product planning. Identify customer needs and translate them into design requirements. Example, the company surveys potential e-bike customers and identifies key needs: long battery life, lightweight design, durability, and easy handling. These customers' needs are translated into specific design requirements such as a battery capable of 60 plus miles per charge, a frame made of lightweight materials like aluminum or carbon fiber, and durable weather-resistant build. Second is product development. Convert customers' needs into technical specification. Example, the customer need for long battery life is converted into a technical specification. A 500 watts lithium-ion battery with regenerative braking. The lightweight design is converted into a frame weight limit under 20 kg, and the durability requirement becomes a waterproof rating for all electrical components. For easy handling specification, may include hydraulic disc brakes for smooth braking and ergonomic design for comfortable riding posture.
Hello everyone. Today I'll be presenting an overview of the design criteria. Design criteria are the specific guidelines and requirements that must be met during the engineering design process. These criteria serve as a foundation for decision making and help ensure that the final product is both functional and efficient. These are the foundation for the decision making, ensuring that the final product is not only functional but also efficient and aligned with our goals. Let's start by discussing the design criteria. Functionalization. Ensuring that the design meets the intended use and performance its required functions effectively. Next, safety. This remains a top priority to protect users and prevent harm during operations. Cost. Managing the project budget and considering the most cost-effective solutions. Aesthetics. The design must be visually appealing, aligning with both users' preference and branding. And last, sustainability. Integrating environment-friendly practices and materials to minimize the product's ecological footprint. Now, when it comes to prioritizing criteria, there are two important methods we employ. Trade-off analysis. Balancing conflicting criteria such as cost versus performance to achieve the best overall design. Often, we encounter conflicting criteria such as balancing costs against performance. This process involves evaluating and making informed compromises to achieve the best overall design. Stakeholder input. Considering the needs and preferences of customers, regulators, and other stakeholders when getting priorities. We always take into account the needs and performance of customers, regulators, and other stakeholders. Their input is essential in shaping design priorities and ensuring the product meets expectations across the board. These criteria serve as guiding principles in our design journey, helping us craft products that are functional, safe, cost-effective, aesthetically pleasing, and sustainable.
My name is Kenneth De Los Santos, and our topic is other criteria in design. AI-based IT system design criteria. Overview AI system. In healthcare, need transparent and reproducible decision-making process. Key focus move from data and information to wisdom driving decision-making. Design approach. Hebner's design cycle applied to AI-based system for ensuring system information and service quality. Challenges. Complex algorithm like GPT require transparency. Debate AI-driven intelligence versus human-curated wisdom in healthcare. Future workshop will explore AI role in medical fields like radiology and surgery. 10-step AI design produce. Encoding transform user requests text image into a low dimensional latent space. Token generation create figure vectors for content. Embedding weight tokens according to context importance. Attention processing focus on essential information from various data resources. Module generation update and tune models like artificial neutral networks. Temperature and sentiment sample measure probabilistic appearance from patterns. Token synthesis generate corresponding text or image. Best output selection ensure optimal text or image generation. Integration and assessment. Perform quality checks using techniques like beam search, decoding, produce machine formulated text image or another output or human use.
The engineering problem-solving process, a structured approach that engineers use to tackle complex challenges systematically. The first step is problem definition. Goal: precisely define the problem by understanding stakeholders' context and requirements. Tools: mind mapping, brainstorming, surveys, interviews, observation, research. The goal here is to precisely define the problem by understanding the key factors such as stakeholders, the context, and the specific requirements involved. Some of the tools we use include mind mapping, brainstorming, surveys, interviews, observation, and research. These methods help us gather insights and ensure we're focusing on the right problem from the very start. Once the problem is clearly defined, we move on to problem analysis. Goal: and identify underlying costs, risks, uncertainties, and areas for improvement. Tools: fishbone diagram, Pareto charts, SWOT analysis, 5 whys, FMEA. The goal here is to identify underlying causes, risks, and uncertainties. We also look for areas where improvements can be made. The tool used in this stage include fishbone diagram, Pareto charts, SWOT analysis, the 5 whys method, and FMEA. These tools help us break down the problem and better understand the root causes. After thoroughly analyzing the problem, we proceed to solution generation. Goal: generate multiple ideas without judgment. Select the best solution based on defined criteria. Tools: morphological analysis, scamper, trees, brainstorming. The goal is to generate multiple ideas without judging or dismissing any of them initially. It's important to consider all possibilities before narrowing down options. Some of the tools we use includes morphological analysis, scamper, trees, and traditional brainstorming. Prototyping is also a common method for testing early concepts.
So overall, managing engineering design requires an understanding of various methodologies, from system engineering to concurrent engineering and finally control system. It's not just about solving problems, but also about doing so within a framework that ensures the solutions are safe, efficient, and reliable. I hope this report gives you a clearer picture of the design processes that underpins much of what we see in the world today. Thank you.